Okay, welcome everyone. So today I'm going to talk about a talk, or I'm giving a talk that I gave really live. But as usual, having a live talk is difficult to record, or at least the recordings never really work out all that well. And I rather do it here in my own studio, which has an advantage and a disadvantage, obviously. So it's a bit higher quality. That's usually the advantage. But of course, there won't be any questions. So it's very hard for you to interrupt me and ask a question, I guess. You can put a question in the comment, obviously, but that's less exciting than just stopping me and asking a question. In particular, for this talk, I got a lot of questions, a lot of really good questions. Thank you so much, by the way. So yeah, it's actually a little bit more interactive if I do it live, but what can you do? Anyway, so I gave a talk here about the not invariants. So how good are not invariants? Essentially, I wanted to call the talk kind of advances or history or perspectives in low-dimensional topology. But since I'm not a low-dimensional topologist, it's a bit difficult for me to have the title and talk about it like that. But it's really kind of my biased perspective, my kind of really biased perspective. I can repeat myself, biased perspective. Kind of trying to kind of go through the history of the subject and how it changed over time, how I got into it a little bit, and what type of questions I see coming up in the future. And it will be fairly interactive, but again, it's much more fun if I do it live, but that's just the price we have to pay, I guess. Yeah, so let's go into it. So I'm going to talk about quantum invariants, and I'm trying to tell you a little bit where they come from without really telling you where they come from, but maybe more how they affected the low-dimensional topology or topology in general. So topology started with a famous series of papers, which Poincaré called, so let's try to do this, analysis situs, which was the original analysis situs, which was the original name for topology paper. Very good. Or a series of papers which Poincaré published with several comments on it, because there were several changes. But it was undoubtedly one of the most important papers, let's say, of the last century. Right? So let's count 1899 as the last century. So one of the most important contributions to mathematics in general. It essentially opened the field of topology. So all of the famous things, but fundamental group, homology or something, they're already somehow in that paper. In particular, there's this famous conjecture, the Poincaré conjecture, which we're going to talk about a little bit as we go. Well, kind of is my starting point here. So this was one of the 1903. We just said the first one was in 1899. So this was like one of the comments on the paper. And in that paper, you will find, you don't need to read French, by the way. If you want to read the paper, there will probably be a translation. I haven't checked. But for this video, you don't need to read French. The one word you will understand is question. And this is like the Poincaré conjecture, which actually was a question. And I'm trying to explain a little bit why it was a question and a conjecture. So people later changed into a conjecture. I guess because it's just nicer if you prove a conjecture. Just answering a question is maybe not as exciting as proving a conjecture. I really don't know. But anyway, essentially the conjecture was, about three manifolds. So two manifolds of surfaces, like a sphere, this is supposed to be a sphere, or a torus, this is supposed to be a torus, or whatever. They were already known a long time before, and they were kind of easy to classify, easy to study. They're given by the number of handles, kind of a classical result, even before Poincaré. And this is like the two-dimensional picture. So if you, the one dimension is very boring. So if you understand two dimensions, then the next step is three dimensions. And yeah, so Poincaré already thought that this is probably very difficult and asked a question instead, which comes down to this statement and essentially saying everything that looks like a sphere is a sphere. So simply connected, we've already seen that here, this is by the way one of the best pictures ever. Simply connected means you can shrink every circle on your space to a point. So here, if you do this trick with the two sphere, which is just a soccer ball, you have the belt, or the equator if you want, or the world, right? You have the equator, and you can actually pull the equator over your head and shrink into a point. That's called simply connected whenever you can do that. So, in Poincare conjectured, whatever. Whenever that happens, actually the three-manifold is trivial. Also trivial in the sense it is the sphere, right? So everything that looks like a sphere is actually really a sphere. So if you want to kind of, this is kind of difficult to imagine. So all of I'm going to do is kind of interesting because it's kind of difficult to imagine, but eventually you can still formulate it in combinatorics. So a three-dimensional manifold, a three-dimensional object, you would think it needs 3 dimensions to live in, but essentially it needs 4 dimensions to live in. And my example is usually if you take the line, which is clearly a one-dimensional object, yeah, R, and you add a point at infinity, which really just means you grab your line, right? You grab your line and you wrap it up to infinity. Then you get a circle, right? You get something like that. You grab the ends of R and wrap them up to infinity, and you get the one-dimensional circle. And the one-dimensional circle is a one-dimensional object, but it naturally lives in a plane, so it naturally lives in 2 space. Similarly, a two-manifold usually naturally likes to live in in 2 space. And if I can grab it, then I actually have a nice picture for that. So it should be the spherical projection. So let's try to find that spherical projection. Do we find a nice picture of the spherical projection? Something like that, yeah. So we have a nicer picture somewhere. Yeah, well, this is kind of the nicest one. So you take the North Pole and you draw a line from the North Pole to the plane, and this kind of projects, that will intersect the sphere in one point and will project the sphere to the plane. Or the other way around, you take the plane as before, you grab it up like a bag at infinity, and then you have, so the plane is a 2-dimensional object, you grab it up at infinity, and then now it naturally lives in 3 space. So a 2-dimensional manifold naturally lives in 3 space, actually. So a 3-dimensional manifold naturally lives in 4 space, and it's like really hard to imagine. My picture that I have in mind is usually like a movie, right? So the soccer ball, if you just cut it horizontally, it's like a movie of those pictures. And the 3-dimensional sphere is a movie of a soccer ball, where in each slice you actually see a soccer ball. So my 4th dimension here is the time. Anyway, so it's kind of really difficult to imagine, right? So not quite clear how to attack this problem, and maybe that's also one reason why this is so difficult. Huh? And it turns out that the answer to the question is yes. And this is one of the Poincare conjecture, maybe you have heard about it, is one of the Millennium Prize problems, and was famously solved very, very late in dimension using Ricci flows in dimension 3 by Perelman, like 100 years after the question, not the conjecture, the question was asked. So it's really reasonably difficult. Turns out higher dimensions are a bit easier. Essentially, you have more space. So Field's medal for Smale, solving it in dimension bigger than 4, and for Friedman, solving it in dimension 4. And then Perelman, solving it in dimension 3. And as I said, dimension 2 is boring. So that kind of solved the problem, solved the question. Took about 100 years. So it's not trivial at all. This funny thing that it's most difficult in low-dimensional spaces, I will try to explain why, but essentially you can just think of the questions people ask. We live in 3 space, right? The questions people will ask are naturally questions that are most difficult in low-dimensional spaces, because essentially our brain is not good enough to ask the correct questions about high-dimensional manifolds. So Poincare conjecture, and I will now try to explain why this, or kind of try to illustrate why this is so difficult. Right? Keep in mind, low dimensions here are really, really difficult. So dimension 3, kind of terrible, very difficult. And the original conjecture of Poincare, conjecture, and it's again in quotation marks, was actually homology detects. So homology is this tool from algebraic topology. Homology detects the 3 sphere. And that's just wrong. It's just very wrong. And that's the whole problem why this is so difficult. So people have developed, in particular Poincaré, this tool of homology, which is like a really good way, or kind of, and it's mapping a topological problem to a linear algebra problem. And linear algebra is very powerful, right? Linear algebra helps you to solve a problem. But it's actually a pretty bad invariant. So something that shocked me a lot, well, I'm very naive. So you see an algebraic topology class, you learn about homology, and you see it on spaces, and it always saves the day. You can always detect all your spaces. But this is just because in a lecture, the spaces are actually very carefully chosen so that this works. Homology in general on topological spaces is pretty bad. And Poincaré already knew that. So Poincaré found a counterexample to this conjecture that homology detects the sphere. And that's why I changed it then into another conjecture, into a question, I guess. That's maybe why it's so carefully formulated. And the way Poincaré did it was reasonably complicated, and I show you a nicer way how to do it using a more modern language. So essentially Poincaré did the following. You take a dodecahedron and you glue opposite faces together. So you glue that face to that face in this planar projection here. You glue that face to that face, and so on. And then you create a three-dimensional object, which you can't imagine anymore because, as I said, it lives in 4 space. But that thing has the same homology as the 3 sphere. So it's not a 3 sphere. It's kind of a very strange object. But it already tells you that it gets a bit difficult and complicated, because if you glue your pictures correct, so kind of glue these objects in 3 space together in kind of a strange way, you will get strange things. And that's something you can't do in 2 small dimensions. Yeah? And this is just where everything gets very, very crazy. If you remember my spherical projection, it's essentially also a gluing of the plane, right? But it's a very naive gluing, and you get a nice object. Essentially, all 3-dimensional manifolds come from such a gluing procedure. I will be more precise in a second. But yeah, so the original question, homology detects the 3 sphere, it's just plain wrong. It's just very wrong. Homology is a really bad invariant of topological spaces, which, as I said, shocked me a lot, because somehow how it's presented in a lecture, it's kind of the opposite. You kind of get the feeling it's the perfect thing ever, while in reality it's not. It's really not. I mean, it can't be, right? You have topological spaces, and you map them to linear algebra. Somewhere along the way, you're supposed to lose information. Right? Key problem for all of the Poincaré conjecture is always like the standard invariants Poincaré essentially developed, and several people after Poincaré developed in algebraic topology, homology in various incarnations of homology, Euler characteristic, whatever. They're really not good invariants. They're really not good. And this is really one of, I say it again, it's kind of very strange, and it takes you a long time to understand that they're actually pretty bad. But if they were be good, it's kind of very easy. Let's say they would be good invariants, then Poincaré would have probably solved everything already. But no, they're pretty bad. It's very sad. They're computable, but pretty bad. And that's a key problem for all of like low-dimensional topology. The standard invariants, they're not that great. They're really not that great. And yeah, enter knot theory. So knot theory didn't come up from Poincaré. Well, I shouldn't say Poincaré didn't knew knot theory, but somehow it was not a topic on Poincaré's head, I would guess. But in the end, this is essentially what Poincaré would have needed. So I'm going to explain that now. So a knot is really just a projection, some string in 3 space, and you nicely project it to a plane. So really, a knot is this type of thing. Nice. So here, just a string in 3 space. Let's watch a video. Let's watch a video in a video. That's very good. And you can bend it and stretch it how much you want. And really, you're free to do whatever you want. That's topology. The only thing you need to do, you can already see it. You could undo it if you don't bend and put the ends together. So for mathematicians, a knot is just glue the ends together. Fine. And there's a theorem in mathematics that everything essentially is supposed to be knotted. So if you put a string in a box and you shake the box, in the limit over time, the string will be knotted with probability 1. And everyone knows that very well. If you ever had a cable, they like to knot itself. Anyway, so knot theory is kind of the mathematical study of those objects, and you're allowed to do whatever you want with them, but you're not allowed to cut them open, right? So you're not allowed to cut them open. Otherwise, as I said, you could just undo the knot. That would be a bit boring. And you study them by those little shadows. But anyway, this is kind of a three-dimensional picture. And nowadays it's like super applicable. It's really unbelievable. So here is a picture I stole from a biology paper. So this thing here, green is maybe not a good color here. This thing here is a protein, and under the electron microscope you will see the shadows of the protein. And the protein is just really, again, a very long string. So if you shake your box, as I said, it will knot itself with probability 1. And how it's knotted affects how it is, its chemical properties, essentially. So another lie, well, not really lie, but another thing it took really a long time to understand in chemistry, it is not just about what the elements of your compound are. I mean, that's true for very, very small compounds, but the larger the compounds get, it actually gets important how they sit in space. Right? And again, if you just think of forming a long string, strings will knot themselves. So a lot of properties of longer proteins, longer molecules, like proteins or DNA, are determined by how they sit in space. And this is really what people do in research. So here's DNA. So the top row here, you see like DNA pictures from the electron microscope, and then people need to, its properties essentially depend on how they are knotted. So what biologists would like to do is they would like to figure out what knot it is, right? They would like to map it to a nice presentation of knots. They really do that. So the knot theory has become one of the most applicable fields of mathematics. But originally it was studied for very different reasons, just because it's fun. And it roughly started in the 1920s, which is quite a bit later than Poincaré. But essentially, knots and links, that's what people figured out later, is what makes Poincaré's original story so complicated, because they're the building blocks of all low-dimensional manifolds. Yeah? So building blocks of low-dimensional manifolds, knots. And the problem in knot theory was, again, the same as in algebraic topology. Essentially, you only had algebraic topology, so you only had invariants from homology theory, some versions of them, and they're just not good in knot theory. They're not particularly strong, and people studied those for I just decided to start knot theory from 1900 on, but anyway, started this for most of the time of knot theory. So let's say for 80 years, people just studied knots under the kind of umbrella of homology theory, and it's just not getting you anywhere. It's just very, very sad. So all of the invariants you get, they are not really good. They're really not all that great. So knot theory, the same problem as with the Poincaré conjecture, and essentially the same problem. So knot theory, very difficult. So even unknotting is difficult. So even this problem of unknotting something is really difficult. Let me see whether I can find the bigger picture here. I can. So this is the unknot essentially, right? But you can't see it. You need to do some very non-trivial manipulations to kind of see it. So even the problems like, is this the unknot? The unknot is just a circle unknotted. Is really, really difficult. And there were no tools. There were no tools around to really attack these types of problems, which is a huge problem, of course, for the field. Right? Well, not many tools were around. Most arguments were somewhat done by hand. A little bit of an annoying thing to do. And yeah, so how is this related to the Poincaré conjecture? Well, a little bit later than Poincaré, mostly due to Dehn, and then made more precise in the 1970s and 80s, is the following idea. So a knot complement is really just to think of the knot as sitting in the 3 sphere, or in R3, it doesn't really matter, the difference. So it just sits somewhere in 3 space. Yeah, let's say in S3. Or in R3, don't worry about the difference here. You can always add the point at infinity, doesn't really matter. So you have your knot somewhere. If you thicken your knot, you get a torus, and the torus is now very, very knotted. And it's really just a picture, knot. Maybe I can actually find a nice picture. Knot theory. How can I spell? Theory, rope, mass. Let's see whether I can find something nice. So it's really, yeah, maybe this picture. Yeah, so knots, and this is, if you think of them as being infinitely thin, but if you thicken them up a little bit, it's more like a rope, right? And a rope is a torus. Yeah, a rope really is a torus. Do we have any this one? Maybe. So it's really kind of a bigger type of object. Yeah, this picture is not so bad, right? It's like a torus that is kind of wind around. And, it's a torus. So if you think about a thickened knot, you just have a torus. In this picture, it's kind of visible as well. Okay, a thickened knot is a torus, which sits somewhere in your space. Yeah. So the idea is now, like very similar with the dodecahedron, you just do some gluing and you get a three-manifold. So your knot sits somewhere in space. You take it out, you glue it in again. Take it out, glue it in again. Okay. If you do that, if you remove a knot and glue it in again, you've done nothing, obviously. But if you remove it and glue it in again, twist it, there's some change, right? Now it's a little bit changed. So what you're doing is we take out the knot and we glue it again in the same. It's empty. There's no hole in space, yeah. And we glue in the knot, kind of twisted. Yeah. You can kind of think of it as like it has some torus, and maybe you just twist it a little bit and put it in again. Yeah. Okay. And the way to encode that is the following. So here I think about my knot as being just a torus. And theorem, the oldest gluing procedure really just depends how well you send the meridian of the torus, of the knot. So here, somewhere there's a meridian, M. And you want to glue in the knot again, and you only need to keep track of where you glue in the meridian. So you glue it to some new curve gamma, which winds around somewhere around the old picture, right? I've now taken out this torus here, so it's gone, and I glue in a new torus along gamma. Yeah, that's what I do. And gamma is determined by how often I go around the longitude in the meridian. And I just get two numbers that determine how often I go around. Here I go around once the longitude, right? I go around once in this direction, go around once in this direction, and I go around 3 times in that direction, so 3 and 1. So I have two numbers that determine my gamma. And the theorem is then that the whole surgery process, the result, it only depends on those two numbers. Yeah? A knot plus two numbers, P and Q. And actually an even stronger result would say it only depends on the ratio, so on the rational number you get essentially. So we take out the torus, we fix gamma determined by P and Q, and we glue the meridian onto gamma. And then we have the big theorem that people discovered. As I said, essentially this is called Dane surgery. Later on it was, well, let's say the early 19th century, early 20th century, then later in the 1970s and 80s, what was even kind of revisited and made more precise. But anyway, any three-manifold is obtained by Dane surgery. That is, pick a collection of knots, pick those surgery coefficients, P and Q, so how you want to glue them in again, and do the remove insert type surgery. So and the only thing you need to study, essentially, are pictures of knots plus a label on them. And the label is the rational number for the surgery. And that is now a three-manifold. So a picture of a knot plus a label is a three-manifold, which is much nicer to think about. But it also tells you now why this three-manifold nonsense is so difficult, because it's not theory even plus, right? Not theory worse. And every such thing gives you a three-manifold, so there are many three-manifolds, like many three-manifolds. I hope that's reasonably clear. Huh? Okay, so there are many three-manifolds, and so the whole question boils down to some knot theory. So low-dimensional topology is knot theory. You can do the same for 3, for 4, and 5 manifolds with some caveat, which I'm not going to talk about. But anyway, low-dimensional topology is mostly about knots. Yeah? And in higher dimensions, you don't have any knots anymore. So somehow this part of the story gets easier. And yeah, knot theory was really not in a good state in the early 20th century. So even questions like, can you distinguish those two, right? So the only difference here is that the crossings are reversed. They're called mirror images. It's really like you have this knot in your hand, you hold it in a mirror, and you see the other one. So if you have the red one in your hand, and then the green one is a mirror, and if the green one in your hand, the red one is a mirror. So if we want to study three manifolds, we somehow first need to study knots. You know? We don't need to. There's a different approach to three manifolds, but at least from this perspective, we are supposed to study knots. But even a question like, can you distinguish those two, is not easy at all. There was no knot invariant that could do that. There was an argument by Dane, like by hand, that they're not the same. You can do that. But there was no good way of doing it, right? Homology will fail or whatever. All the homological invariants won't do anything. And yeah, so even such a question like, are those the same? Nobody knew. It's kind of an interesting type of part of the story. And then really a breakthrough. The Jones revolution, like in the up to the 1980s, people only studied knot theory from this perspective of homology. And in 1985, just Jones came around, and this was really a shock. So completely out of the blue, Jones came around and produced a new invariant of knots, which was different. It didn't came from the usual homology tools. It came from representation theory. It's kind of very strange, and people call those the quantum invariants nowadays. And it essentially revolutionized knot theory at that point. So, for example, it easily distinguishes those two, right? The invariant was the first one who easily distinguishes those, and not just those in any mirror image. And not just that Jones came around and said, oh, there's a Jones polynomial, which nobody has seen before. Well, Jones didn't call it the Jones polynomial, by the way. But anyway, there's this invariant called Jones polynomial that nobody has seen before, which can do a lot of fancy things in knot theory. No, not just that, but also people realized very quickly that the Jones polynomial is just the tip of the iceberg, and there's actually a zoo of those invariants, right? So a zoo of invariants attached to any semi-simple Lie algebra and any representation. Infinitely many, a lot of them, right? So going from, we have not enough invariants, Jones came, and then we had infinitely many, the Jones revolution. It's just really strange. There's also a categorification story, and it really is a very big story. Like Hovanov is the big name here, categorifying the Jones polynomial, like a homological invariant. But this was really weird. So people got really shocked or really excited, whatever you want to call it, right? So a completely new approach to knot theory, and therefore somehow people expected a completely new approach to things like the Poincare conjecture and friends. It's called quantum topology, right? Quantum things. So the quantum here comes from the name because those guys come from quantum groups. Don't worry about it too much. It doesn't matter. A new type of invariance that came out literally out of nowhere. So people were really, really shocked or excited, whatever you want to call it. They were so shocked or excited that Jones just got the Fields Medal for this discovery. It just came out of nowhere. Astonishing relationship. Jones actually came from not just representation theory, but from functional analysis, if you want, from the study of von Neumann algebras. And yeah, so Fields Medal, absolutely deserved. It's absolutely crazy. So usually if you go through the list of Fields Medals, it's like you read whoever discovered X and discovered Y, and you just think like, yeah, that's pretty brilliant, but I couldn't have discovered that. The Jones polynomial is one of the only examples I know where you really think the Fields Medal, if you just read the definition of the Jones polynomial, it's essentially trivial. It's kind of fun. You can explain it. I will not do it. It takes too much time. But you can essentially explain it to a high school student. No problem at all. You can just explain it to a 5-year-old if you want. Really easy. And it's really like this feeling like, oh, I could have done that. Of course, that is an illusion, right? There's some brilliance in discovering something easy. But the whole point here is that the Jones polynomial is like this very easy tip of the iceberg invariant that people have missed for 100 years. It's absolutely insane, right? So there is something that is so easy, I said again, that you can essentially explain it to a high school student. But researchers have missed that for 100 years, 100 years, right? It's very different from most Fields Medals where it's clear that you can't explain it to a high school student. I don't understand what most Fields Medals do. So, but this one is like absolutely brilliant. And it's ridiculous. It really comes from so many different perspectives for Neumann algebras, topology, representation theory, geometry. It's just ridiculous. So people love it a lot. And it's called the Jones polynomial. And as I said, there's a whole zoo of them, Jones polynomial types. Okay. And And yeah, so this is how I entered the story. And I've spent like a quarter of a century studying them. But somehow it never crossed my mind, because they're so beautiful and everyone was just like, really, really excited. It never crossed my mind to actually check how good they are as invariants. Yeah? So it's kind of the very, very same thing as this happens with homology. If you study homology and you learn it in algebraic topology, you just see it on the easy examples, and on the easy examples it will do very well, right? But it doesn't mean it does well in general. No. It is actually pretty bad in general. Yeah. So in our little friend homology, where was it? So here, just every surgery on a knot where you grow meridian to longitude gives you a 3-manifold, which is not the 3er, but has the same homology. Yeah? So every surgery on a knot where you're gluing meridian to longitude, gives you a homology sphere. So this proved to Poincaré's original conjecture. Say that again, homology is really bad. Every knot that you take and you do surgery, gluing meridian to longitude, gives you a homology sphere. So homology is really not that great on manifolds. You can also check that they're essentially all different, right? That's another question you might want to ask. But somehow it never crossed my mind to try to do the same with Jones type invariants, the quantum invariants, whatever, several of them. Never crossed my mind. Remember that you have the whole zoo of them. It never crossed my mind to do it. I can't tell you why it never crossed my mind, but I decided to do it eventually. Huh? Nobody actually checked how well they actually perform, and yeah, so let's do that. Turns out that it's like the very same story as with homology. They're pretty bad, but in some sense, homology is still very well studied because it's just good itself, right? Not just as an invariant, right? The Jones polynomial. The Jones polynomial is fantastic because it relates many fields. As an invariant, it's not that fantastic. Okay, let's just be realistic. It's not that fantastic. Okay, and let me just briefly explain to you how to construct the Jones polynomial and friends. It's not super important. From now on, we more go into this type of idea where we just run. I just show you the results. You need to believe me. We need to believe me. Oh, you don't need to believe me. You can just Google it. But anyway, I will be less precise, I guess. Anyway, so essentially you write a knot in this nice presentation, and every little slice is now a cup or a crossing together with some strands, and each one of them corresponds to a matrix, and just compose all of them together gives you the corresponding invariant, right? You start from an empty space here, which is just a ground field. You go to an empty space here, which is just a ground field, so you get a composition of matrices that end up in the ground field. It's like a pairing if you want, and this is the number, and the number is your invariant, and this works for any choice of R from this matrix R. So the matrix you associate to a crossing is usually called the R matrix, and those R matrices usually come from a pair of a semi-elliptic Lie algebra and a representation. So just to be completely explicit, for example, for the Jones polynomial, the matrix would be that thing. Okay. For q equals 1, this is just a swap map, right? For q equals 1, this term dies, and it's just 1, 1, 1, 1, just swaps, right? So Jones is associated to SL2, and what you see here, you don't need to know that. But anyway, what you see here is like the two-dimensional representation of SL2. So every semi-simple Lie algebra and every representation gives you a similar matrix that you just run in your machine, and you get a composition of matrices, and the composition will be a number, and that number is your invariant. And that works for any Lie algebra and any representation of it. So there are infinitely many. And it's not just infinitely many, that's essentially infinite times infinite, because if you already fix SL2, you have already infinitely many choices, because you can vary just the representation. Yeah, that's what I mean by a zoo of those. It's really a lot. So really a lot of those. And I just wanted to compare them, some of them, and essentially I just put Jones in the middle because everyone likes Jones. I put Jones in the middle, the Jones polynomial, and I compare it to various ways to make it nicer So I could compare to, so the Jones polynomial, the two-dimensional representation of SL2. What I call the B1 invariant is a three-dimensional representation of SL2. I could go to SL3. I call that the A2 invariant. I could go to the categorification, as I mentioned before. It's the same type of object, but now categorified. So my third number here is whether it's categorified or not. Or I can change to a different Lie algebra, GL11, and I get the Alexander polynomial. And so kind of many ways to do it. Start with Jones. I could change the representation. I could change the rank and make the group bigger. I could go to the categorification, or I can even change the type, the Lie type, if you want. And I just wondered what was interested in how they actually perform on knots. And we're very lucky. There are many, many knots, so you can just list them. So if you just want to do that, it's just people just did that for a long time. Table of knots, and we'd probably find some. You can just list them and give them names. So you can order them by the number of crossings. Can you zoom in here? Oops, no, that's not what I want. Maybe this one. Can we zoom in here? What the hell? We just zoom in. How annoying is that? Table of knots, this one. Can we zoom in here? Hopefully we can. We can zoom in, that's fine. That's better. Okay, so you just list them by the number of crossings, right? Unknot, 0 crossings. This one is the only one with 3 crossings. There's only one knot with 4 crossings. There are 2 knots with 5 crossings. And you just order them in an arbitrary way, 1, 2. There are 3 knots with 6 crossings, 6, 1, 6, 2, 6, 3, and so on, right? So you can just list them. And it turns out that the number of knots grows exponentially in the number of crossings. So here you can literally see that. You might wonder, this is not an exponential function, but I have a log plot. You can kind of see here a log on the y-axis. 10, and then 10 cubed, 10 to the 5th, 10 to the 7th, 10 to the 9. So there are a lot of knots. Yeah? So the number of knots grows exponentially, which is kind of important because I essentially want to run them over that list and see how well they actually perform. And this is kind of where my story starts. So I've grown up as a mathematician with those various statements about Jones polynomial. I just take its categorification to be formally precise. Yeah, so this is about Kobanov homology, but I will ignore the difference. Yeah, that's maybe not completely fair, but let's just ignore the difference for this video. So just Jones polynomial. Anyway, I've grown up with many of those results that you like. In algebraic topology, you learn homology and you apply it to easy spaces, and it's like a perfect invariant on easy spaces. And in knot theory, something similar happened, which kind of made me not quite realize what's going on. Yeah. So Jones polynomial on simple knots is just perfect, essentially. And one of those statements, which is like really, really good, is this theorem by Cronenberg and Mofka that the Jones polynomial, as I said, I will lie a little bit, the Jones polynomial detects the unknot. But what that means is whenever you feed in something that is not the unknot, you will get a non-trivial invariant. Yeah? And there's this really beautiful ICM talk that we can probably just Google. So Cronenberg and Mofka ICM 2018. Let's see whether we can do that. Cronenberg, Mofka ICM 2018. Let's see whether we can actually find that one. Maybe this one. Knots in 3 manifolds. Cronenberg and Mofka, beautiful. So that's what I was looking for. And it's kind of a fantastic, a really beautiful talk. And they do it in tandem. Still the same. They do it in tandem. This is another one. Okay, so let's maybe... Yeah, they do it in tandem. It's very, very exciting. A really nice talk. And it's, well, wonderful model. You just heard it. It's really, really beautiful. Please watch it. Excellent, excellent talk. Anyway, so there's this statement. Kobanov homology detects the unknot. Jones polynomial detects the unknot if you want. And it's one of these statements which is like absolutely important, obviously, but it's somehow misleading in the bigger scheme of things, as I know it now, right? Homology again, perfect invariant on easy spaces if you want, but in the greater scheme of things, it's actually not all that exciting. Fine. And Same will happen for the quantum invariants, and I found that very shocking when I just realized it. Anyway, so here's how it goes. My first measurement of how good are quantum invariants, title of this talk, how good are quantum invariants, is I put all of them in a bag. If you don't know what a prime knot is, by the way, forget it. Just forget it. Just put all knots in a bag, and I grab out one randomly. And how likely is it that it is kind of detected by let's say the Jones polynomial or the various variations that I was talking about? So how likely is it to be detected by those other things, right? So how likely can I distinguish it from all others? Right? Essentially very important if you want to write down one of those tables of knots, yeah. And if J would be, let's say, a Jones polynomial would be a perfect invariant, you just run it over those knots, and you can just make those tables, right? You can just tell whether the knots are different or not. Okay, life isn't that easy. So probably not a spoiler at this point anymore. Life isn't that easy. We'll see the precise data in a second. So formally, I want to know kind of the limit of the different Jones polynomials over all knots I expect. Let's say smaller equal to n crossings. Yeah, we go through this list of knots up to a certain point and just count how many different polynomials we have and compare them to how many different knots we have, right? So how good is it in detecting knots? That's essentially the question you can ask here. And there are a lot of results in this direction, all very important, actually beautiful, but somehow again misleading. They're all for somehow small knots. Yeah, coming back to my I know I sound like a broken record. Very sorry for that. But coming back to my story about homology on easy spaces, something similar like that. Easy spaces, knots with a small number of crossings. The trefoils, right, for example. So all of these are detected. How does a big story work? How does it really go if we go into the kind of the realm up here? It's kind of the high number crossing knots. And again, I will do it only up to 16, but let me just say that 16 crossings is actually not that much, if you think about it. So let's see what happens for 16 crossings. So it's a very disappointing result. So already for 16 crossings, most of them do very, very badly. Yeah. So let me just pull up the corresponding. So everything is online. We have put everything nicely online. So not me. Victor Zhang actually is really a magician doing that. Let me just open the page, and then you can. So here, this is the name. Yeah. So you can just Google it. You can just Google it, or I just put it here. So there's a nice website where all the stats, for example, are connected. So how many unique things does it take? Okay, we can zoom in here. So here are the various things. Alexander, I can just turn off all of them except Jones, let's say. Yeah, Jones polynomial. On 16 crossing knots, it only takes it only can distinguish half of them, which is not really all that great. And this curve goes to 0 exponentially fast. And it's very, very sad, actually. So it's like with homology. It's not terrifically great. You know? Categorification is really not much better. It takes 54%. And what I find very, very disturbing, if you take all of them together that I tested, all of them together are only at 84%. That's not good. That's really not really all that good. And still this curve goes down exponentially fast. And the very annoying thing is that all of them together are essentially the same as the B1 invariant. I will go back in a second what the B1 invariant is, right? So 84 versus 83.8. So it's very, very sad. They're essentially all the same. It's very disappointing. So, yeah. So I studied them for a quarter of a century. And I was always convinced, I don't know how you feel, but I was always convinced that these are really good invariants. Somehow they're not. They're at least not good from this perspective of how they distinguish knots. And yeah, so essentially you just run it, and then you can actually prove that statement. So we can actually prove that they distinguish knots with probability 0 if you want. For strictly speaking, I can't prove it for all of them, but for Jones, for example, I can. And this is like really exactly the opposite of that, right? So it distinguishes knots with probability 0. very disappointing statement in some sense. Okay, and it gets even worse. I will explain that plot in a second. I put it up anyway. The computational complexity is pretty bad for them. So n is the number of crossings. So they're not just bad invariants in some sense, but they're also hard to compute. It is a bit of an annoying thing to say. So Jones polynomial, for example, is roughly around 2 to the square root of n, where n is the number of crossings. It's not that great. But you can see somehow here in my little plot. So I told you just B1 is the best, but B1 is also the most expensive one. I'll explain the plot in a second. While Jones is pretty low. So let's go to the plot. We can also do that on the website. It's a bit nicer. So we can just open it. And it's a box plot. If you don't never seen a box plot before, the line in the middle is like the average, and 50% of all knots are in the box, right? So the smaller the box, the better, because the box is like the 50% thing. So 25% above the average and 25% below the average. And it's very laggy. It's a very, very large picture, and you can see it here for B1. What happens is that there are a lot of outliers, so knots that took a long time to compute. Yeah, so let me reload the page because it's very laggy now. So let's wait. So this is again a log scale. So something like Jones is like a universe faster. So the most difficult knot in Jones took like 0.1 seconds to compute, and here we are at 100,000 seconds. So log plots are very scary. Okay, so almost all the computational complexity is in the B1 thing, and it was so bad that we actually needed to rewrite. Again, Victor did that. Victor is a magician. Rewrite the R matrix into another program, which did worse on average, as you can see, but had fewer outliers at the top. So it helped us then to kind of break down the computational complexity of the problem. So essentially what you see here is that all of them are bad. So if you look back to this picture, all of them are bad, and they drop down exponentially fast, and they're kind of oppositely ordered compared to their time complexity. So the more difficult ones are also the better ones. Alexander is the fastest and the worst, something like that, which is somehow really disappointing. So they're difficult to compute. They are computable, that's good, but they're difficult to compute and not all that great. So really, quarter of a century wasted? I don't know. At least from this point of view, it's not all that great. Sometimes in mathematics, you just need to communicate negative results. It's a little bit annoying. But at least it opened a new question. Oh, by the way, so Hovanov should specialize to Jones. I haven't explained that. But the computation was better. It was faster, and that's simply because we used a different program for Hovanov, which ran in a different language. So changing your programming language actually makes things better. So I will not really shit on programming languages, different ones here. So let me not explain which one is which programming language, but changing the programming language is really sometimes a game changer. Just to make that clear. Yeah. So let me just skip that, but you can also have a different type of idea of what it is to be a good invariant. But let me just skip it. So the real question that arises is, okay, if they're all bad in some sense, maybe we can somehow compare them, right? It's not so much about saying this is good, this is bad, but more like let's compare them. If infinitely many of them, there must be some nice way of comparing them. And maybe we can literally see why they're bad or not. So let me just explain this idea from topological data analysis. The shape of data, right? You have some data and you want to know, oh, it's a line or a filled circle, or is it more like an empty, like a real circle, so a ball or a circle. And so what shape are the quantum invariants? Seems to be a natural question. So what I do is I take my Jones polynomials. Here's on the list of knots. And they're just vectors. They're polynomials, but you just collect the coefficients. So they're really just vectors. And you put them in a high-dimensional space, where you just pad with zeros so that everything kind of lives in the same space, right? So you just put them as vectors into the same space. In this case, it's an 11-dimensional vector space. Yeah, so you just do that, put them nicely in 11-dimensional space, and then they form like a point cloud, but now let's say in 11 dimensions. Cool. So you now have a point cloud of polynomials. Beautiful. So what do you do with that? It's kind of a nice idea as a mapper algorithm from topological data analysis. So if you point cloud, you choose a little radius of a ball. You have little balls around your points, and whenever every ball now you collapse to a vertex, so every ball you collapse to a vertex, and you draw an edge between them if the corresponding balls overlap. Right? So this point cloud here gives you that graph for a certain epsilon. This point cloud here gives you that graph, right? So how do you do that for the Jones polynomial, for the polynomials? We'll see actually how that goes. And they form these fantastic structures, which you can again play live. So let's go to the ball mappers. Let's say Jones versus Ovanov. Let's just select them both. It's a bit laggy. So Jones forms this beautiful pattern. So these are all the Jones polynomials, and they form this fantastic pattern in this high-dimensional space. Very, very beautiful. And yeah, so you can zoom in, you can move it. Here's Ovanov. Interesting. Almost as these alien type patterns. Very, very strange. And now we can do the following fun trick. We can, for example, see all of these knots up here. So every bubble here is a few number of knots, size 10, size 15, whatever. Here are more knots in the middle, size 50,000. And you can literally see why it's bad in distinguishing things. Because the things that are far apart from everything, they're pretty tiny. So these are knots with very unique polynomials. While in the middle, there are knots with very similar polynomials, right? And there are quite a few of them. Like 50,000 compared to 10, compared to just one here, just 1 or 3 that sit up here. Yeah, so very, very few. But even worse, and this is kind of what is really annoying, they essentially all do the same thing. So I select those here, and I will see where they end up in the other one, in the one-off. And it's the same. They end up somewhere in the same. So the graph is only defined up to rotation. Yeah. So they end up in the same slot. They really do essentially the same. It's very, very sad. We can select it again. So maybe we select something in the middle, something like that, and we compare, and it ends up in the middle and just a little bit further stretched out. So the categorification here is just stretching it out a little bit. So they're all essentially doing the same. I mean, literally, let's compare it to A2, for example. Let's see where it actually goes. It takes a while to load. This is A2. Roughly, again, looks the same. Very dense thing. And we can, again, compare. And you see it's also, again, the same problem. The middle ends in the middle. Yeah. So also they found this, so the size of the balls, I should have said that, the size of the balls correspond to the number of knots that end up identified. Here we identify some of them. Yeah. And the problem is almost all of them have a similar, not the same, but similar type polynomials. Yeah. And they all end up in the same kind of type of thing. The only one that is a little bit different is B1, if you want to check that in yourself, just playing here on those websites. And essentially what happens is the following, and that's something I learned way too late, that the easy knots, the ones that you usually see, that people compute, are at the outside. They have very unique polynomials, right? They're very far away from everything. The bubbles are very small. And the ones nobody really talks about, they're all in the middle, but they're the majority. Like, look at the size of the things here, and we can go back to the website. So they're literally the majority, 70,000 in one vertex, the majority of everything, and they kind of have the same polynomial. And that's essentially a really beautiful illustration, why they are all the same. Huh? And then you might ask, okay, so you only told us negative things. Can you at least tell us something positive? And yes, I can. So let's just look at this coloring, which is a slightly different website. So not our website in this case, a different one. Again, very beautiful. I just pull it up. So in this Center of Topological Data Analysis, very nice. You can do this live. You could turn it. It's a beautiful thing. You can color it and essentially whatever, Jones. So here's Jones. Similar type of setting, and you can color it with, for example, the signature mod 4, yeah, and you will see a certain pattern, right? So if you color it, signature is one of these classical homological invariants. You just color your graph with the signature mod 4, and you can clearly see it is kind of an upper part and a lower part, so a left part and a right part if you want. And you might want to go ahead and prove that, right? So signature, we can also go back. That's for Alexander, it's even nicer. So Alexander is very boring, it's just a line. But signature mod 4 is literally left-right split. And you can go and prove that. So somehow the Alexander polynomial knows the signature, which is a bit surprising because, signature is a homological invariant. So it's not like just negative news. You can literally use that to visualize potential theorems and just go ahead and prove them if they're easy enough. So I really encourage you to look at those, in particular the first side. The second one is just what we did. The first side is really nice for the coloring. They explain how that goes. It's really a nice idea. So you literally just can see relations among the polynomials, right? Not just this type of relation, but also related to other invariants and how they compare. And maybe that's really the future of how you should do it. Maybe some big data approach. That might be just by brute force comparing them like I do it here, or more sophisticated things, and people do that already with neural networks, deep learning approaches. Yeah. I recently talked to a computer scientist, and they said like, oh yeah, times are really changing, and we see more and more papers in topology turning up in our conferences. So for the computer science things, and they usually do some type of deep learning methods. Right? Questions change now. We have all those quantum topology invariants coming from the Jones polynomial. We should rather use some, and we have a lot of them, right? Because there are plenty of them and there are plenty of knots. We should rather use some big data type of approach to compare them. And really the summary is we have a lot of them, as I just said. Quantum topology somehow sits in the intersection of all of the big fields of topology. And before Jones, we had this lack of knot invariants. After Jones, we have actually too many in some sense, right? Like way too many. And they're all the same. So we somehow should try to compare them in, people of course did that, but the times change in the sense that people now not mostly, but there's a bigger trend that people try to compare them using some data type of approach, whether it's, as I said, whether that's deep learning or more classical data science type of thing. Right? So here, the things we already had. So the categorification essentially just pushes things a little bit further away. Right? So all of this helps us to, and it's kind of the point, to compare. No, this was really bad. To compare the knot invariants. Yeah? So that's the whole thing. We have too many of them. Maybe we should really just use comparing and look for patterns. There's sometimes very beautiful patterns that show up. Here's this example that I showed you with the Alexander polynomial, where you can literally just draw a support vector machine, a hyperplane separating the signature mod 2 mod 4 and the signature 0 mod 4 from one another. And as soon as you see this is actually not so difficult to prove, right? So you want to kind of use it for conjecturing, visual data analysis to use it for conjecturing. Similar for the roots. So the roots have a very specific distribution. You can play around on this side. It's actually quite nice. So let's do Jones. So here are the roots of all Jones polynomials connected. The figure is scaled such that the biggest root should be somewhere here at the outside. So very difficult to see. So there are a lot of roots and a lot of large roots around the real axis. This is kind of interesting. And otherwise, we can zoom in. They literally come here. So this is a heat plot. The hotter it is, the more roots. So we count multiplicities. So literally, they just gather at certain points. And this is like this nice heat plot. So if I turn off the heat, you can see that's like spread in this strange shape. And if you include multiplicities, this is so beautiful. You can literally see how the fire goes out and just concentrates on very specific spots. Yeah, and this is kind of true for all of them, whatever Alexander polynomial. It's a bit too far zoomed out. Or one off. Yeah. So literally just comes down to very specific spots. But it's actually quite far spread, right? So, but with multiplicities, almost all roots are the same, which is kind of an interesting type of statement. Yeah, I love those pictures. I can play with them literally all day. But you don't want me to play with them all day. You can do it yourself anyway, right? So this is like the new task I would like to promote here. Now we have so many of them. We should use some tools, like maybe modern tools like AI and big data and whatever, to really compare the various invariants. Right? They're not good. That was the title of the this video, but they're good in the sense that they have nice patterns. They're just not good invariants. They're good in some other sense. Anyway, I hope you enjoyed this video, and I also hope to see you next time.